Welcome to this lecture on heat distribution in buildings. In other lectures, you've learned a lot about the supply side of heat using heat pumps, geothermal heat, and more. You have also learned to estimate the heating demand of a building or a neighborhood. In this lecture, you are going to learn how to couple both sides with the distribution system. To do so, you are going to discover the main parameters of distribution systems relating to the most important choices to be made when designing them. After this lecture, you will be able to make the right choice of distribution temperature, depending on sustainability aims and occupant comfort. You will also be able to make an appropriate choice of the heat distribution medium, water or air. And finally, you will be aware of the different possible combinations of distribution systems. In another presentation, you have learned to estimate the hourly power needed to maintain a building at a certain indoor temperature, 20 degrees in my example. Imagine that 500 watt is needed. Imagine also that there is a radiator, like on the picture, delivering heat to the room. In the radiator, warm water, produced for instance by a boiler, is circulating. It enters the radiator at T supply and goes out at T return, and its average temperature is Ts. We assume the surface of the radiator has the same temperature as the average water temperature. The heat exchange between the radiator and the room air is Q, proportional to heat transfer coefficient, radiator area, and temperature difference between room air and radiator. The radiator must deliver the 500 watt we need. It is therefore losing heat, so the sign is negative. Ti is 20 degrees and the heat transfer coefficient is 10 watt per square meter Kelvin. What remains is a freedom of choice between radiator size A and average radiator temperature Ts. The lower the temperature of the radiator, the higher the needed surface area. In the first example, the radiator has an average temperature of 120 degrees. This could be the case when the heat is produced with an old district heating system. With this temperature, a radiator surface area of 0.5 square meter is needed. In the second case, typical for old boilers in which the supply temperature is 90 degrees and the return one 70, the radiator has an average temperature of 80 degrees, leading to a radiator surface area of 0.83 square meter. In the third example, the radiator has an average temperature of 60 degrees, leading to a surface area of 1.25 square meter, typical for high-efficiency gas boilers. And in the last example, the radiator temperature is only 30 degrees, leading to a surface of 5 square meter. This is typical for modern systems like heat pumps and low-temperature geothermal energy. Why should low temperature be preferred? Well, the higher the temperature of a medium, the more you can do with it. For instance, with water at 40 degrees, you can wash your hands, but you can't boil food or disinfect a tool. For this, you need water at 100 degrees. And if you boil water under high pressure in a boiler, you can make steam at 600 degrees, which can be used to action a turbine, which in turn action a generator producing electricity. 1 megajoule of fuel will produce 0.6 megajoule electricity and 0.3 megajoule waste heat. If you use the electricity to power a heat pump of COP4, you will get 2.4 megajoule of heat, so the total heat production amounts to 0.7 megajoule. But in most gas boilers, gas is burned at around 1500 degrees to produce hot water at 90 degrees, resulting in a total heat production of 0.95 megajoule instead of 2.7 above. This is an enormous waste of fuel resources. The use of high temperature for low temperature application is then a loss of the potential of high temperature. Another reason to prefer low-temperature heating is that many renewable-based heat supply systems have a low temperature. Geothermal energy in the Netherlands has a temperature about 70 degrees. Most heat pumps cannot deliver heat above 50 degrees without losing a lot of efficiency. Solar collectors achieve only a limited temperature of 50-60 degrees. Storage of heat in the ground, like in aquifer thermal energy storage, is at very low temperature, around 20 degrees. Having said this, there is still a major reason why we often cannot switch to low-temperature space heating, and that is because, as you can see here for European countries, around half of the building stock was built before 1980 and uses high-temperature radiators. Replacing these high-temperature radiators by larger low-temperature ones or floor heating is expensive and for many people not affordable. And even if it was affordable, it would lead to thermal comfort problems even if the radiator is large enough to supply the demanded heat. Why should thermal comfort problem appear while we calculated the needed power based on the right indoor temperature 20 degrees and the right but poor insulation values of the construction? To answer this question, we need a little bit more knowledge about thermal comfort. Our thermal comfort indoors is affected by clothing, metabolic activity, air velocity and turbulence, humidity, air temperature, and radiation temperature. Let's focus on the last two. Most people would say that it is much cooler in the shadow of a passing cloud than in the sun, but this is not true. The air temperature remains quite identical, but in the sun your body is also absorbing the radiation from the sun. This radiation is not absorbed by air, which is transparent to solar radiation, but is absorbed by the human body. On the same way that the human body can't feel solar radiation, it can feel infrared radiation from every surface having a temperature TW different from the skin temperature. If the wall has the same temperature as the indoor air, people will feel like Ti. If the wall has a higher temperature, people will feel a higher equivalent temperature. If the wall has a lower temperature, people will feel colder. In order to get a better insight in what happens, it is most convenient to work with an average surface temperature of all walls, floor, and ceiling. The average surface temperature of a room is called the mean radiant temperature, MRT. This figure shows the comfort relationship between the mean radiant temperature and the air temperature. On the x-axis, the air temperature, and on the y-axis, the MRT. This diagram shows that low air temperatures can be compensated by a high mean radiant temperature. For instance, if the MRT is 20 degrees, an air temperature of 19.5 is enough to ensure comfort. If the MRT drops to 17, the air temperature must then be raised to 22. Surface temperature of walls and windows depends strongly on the insulation. In a well-insulated building, the surface temperatures during the cold season are higher than in poorly insulated buildings. This results in less transmission losses and therefore less heating energy. Furthermore, because the MRT is high, the air temperature can be lowered, decreasing even more the transmission losses and the heating energy. This diagram also explains why in cold countries radiators are generally placed under the window. This is because the hot radiator not only brings the needed heat but is also used to compensate for the cold surface temperature of outer walls and windows, increasing this way the MRT towards a comfortable level. In poorly insulated buildings, a radiator temperature above 70 degrees is needed in general. If the temperature of the radiator is lower, this will result in discomfort because the mean radiant temperature is too low. So, when using low temperature heating, a minimum degree of insulation of the facade and windows is needed. One way of transporting heat in a building is to use a network of pipes bringing the hot water and its energy from the central heat conversion system to each room. In standardized terms, the heat conversion system is called the generator. The radiators or floor heating are called the emitter system, and the water pipes, including all valves and pumps, are called the hydronic system. The generator may be a boiler or a heat pump or a district heating heat exchanger. There is a supply pipe in red and a return pipe in purple. This way, all radiators get the same temperature levels and can deliver the same quantity of heat. Even more branches are possible, like here we have 2 floors. In the case of a building with 5 floors, we would have 5 main branches. Up to now, we consider that heat is transported with water. But in many buildings, especially offices, schools, hospitals, heat is also transported by air. To be able to make a choice between water and air as transport fluid for heat and cold, we need to consider the size of the transport ducts. The quantity of heat needed by the room is Q heating. This heat can be expressed very simply by this equation, saying that Q heating is the density times the specific heat of the fluid times its volume flow rate times the temperature difference between supply and return. Let's compare the properties of water and air. The specific heat of water is 4.18 kJ per kilogram Kelvin. Rho is 1000, so rho Cp is 4180. As for air, Cp is 1 and rho is 1.2, so rho Cp is 1.2, quite a difference with water. This difference must be compensated by a much higher flow rate of air compared to water, if we want to bring the same quantity of heat. You see below that the volume flow rate of air must be 3483 times the one of water. What a difference! You see it pictured as size of the pipes. In general, the needed flow of air to transport heat is much bigger than the 36 cubic meter per hour per person that we need for fresh air. To save space in corridors and rooms and to avoid draft by the air system, the needed clean air is heated or cooled in an air handling unit, and the remaining heat demand is provided by a water system, like radiators or floor heating. Let's look now into more details at the transport of heat using air. Outdoor air at temperature TO is fed into the heater of an air handling unit. The heater itself gets its heat from a water heat exchanger connected to the generator, a boiler, heat pump or district heating. The outdoor air is heated to TS and then supplied to the room through a valve where it mixes with the room air. The same volume of air is then exhausted to outdoor, as you learned in another presentation about supply and exhaust ventilation. Of course, a heat recovery heat exchanger can be placed as well. As an example, you could expect such temperature levels. With an outdoor temperature of 5 degrees and an indoor temperature of 20 degrees, TS could be around 22 degrees, compensating this way for all transmission and infiltration and ventilation losses. Let's look at the layout of air ducts. The blue line is fresh air heated by the generator. In brown, you see the exhaust ducts, which have the same size as the supply ducts. So the total space needed is like on the picture. The air is distributed to each floor by vertical ducts. On each floor, there are branches in the corridor and from the corridors to the rooms. A similar layout is used for water systems. Let's make a short inventory of the different distribution systems using a room that you see on the left. On the right, we have the technical room. There is natural ventilation and a radiator connected to the central heat generator, generating hot water that is circulated to the radiator, in which it cools down and then goes back to the heat generator in a closed loop. Observe the valve. The radiators can mostly be controlled at room level. Very often there is also a room thermostat telling the heat generator when to produce heat and when to stop. And of course the radiator can be replaced by floor heating if the building is well enough insulated. In more modern systems, there is a mechanical exhaust and supply ventilation system with a heat recovery heat exchanger between the supply and the return. This is a kind of basic air handling unit. The preheated air is supplied to the room where it is further heated by the radiator. Here too, radiators can be replaced by floor heating. Let's look now at the all-air system, applied a lot in the US, for instance, especially in office buildings, schools and hospitals. In this system, there is no possibility to control the temperature at room level. The temperature and humidity are centrally controlled in the air handling unit, and the air is provided to the room at a preset temperature and humidity. The central heater is connected to the heat exchanger in the air handling unit. The central cooler is connected to the cooling heat exchanger, heating and cooling the air to the preset temperature. In Europe, in general, we use a mixed configuration. The air handling unit is designed to provide enough fresh air, 36 cubic meters per person per hour, and this air is heated or cooled. As the airflow rate is not enough to maintain the building at the right temperature, a substantial part of the heating is done with the radiator below, and for the cooling, an additional cooler above. The central heat generator provides heat to both the water pipe for the radiator and the air in the air handling unit. The central cooler does the same. In summary, you know now that we strive to low temperature heating to be able to make full use of renewables and to make a rational use of energy. You also know that in poorly insulated buildings, low temperature heating can cause discomfort, even though the calculated heating powers are correct. This comes from radiation from cold surfaces. You are aware of the different temperature levels at which heat can be supplied: 70-90 for high temperature, 50-70 for mid temperature, below 50 for low temperature. You are also aware that heat can be distributed through water systems and through air systems, and that both are generally combined, especially in non-residential buildings. Thank you for listening to this lecture.